Everyone thinks NASA is hiding something about 3I Atlas, but the truth is more uncomfortable. The data itself refuses to behave. Every measurement contradicts predictions, every light curve breaks the models, and before they say anything publicly, scientists must understand what they're looking at. And right now, they don't. So, before assuming a cover-up, let me show you what actually forces a space agency into silence. Right now, somewhere in Maryland, inside a windowless building surrounded by security fences, astronomers are staring at numbers that make no sense. Spectral lines appearing in wrong wavelengths, brightness variations that existing thermal models cannot explain, activity patterns that fall outside every framework built from decades of common observation, and they say nothing. 3I Atlas passed closest to our world weeks ago. Millions watched the news. Observatories turned their instruments skyward. Space agencies promised updates. The internet waited for images, for answers, for proof of what this thing actually is. The images never came. The data never arrived. NASA remained silent, not because they found nothing, but because what they found demands something our modern world has forgotten how to do. Wait, verify, be absolutely certain before speaking. What would you do if you were the first person to see data that made no sense under current models? When you search for 3I Atlas today, you find excitement from January, predictions from February, then a strange, uncomfortable quiet that stretches into the present moment. Social media fills with questions. Why no photographs? Why no press conference? Did they see something they cannot explain? Or worse, something they refuse to share? The public expects space agencies to work like news channels. An event happens, a camera captures it, the world sees it within hours. This is how we experience reality now. Instant documentation, immediate sharing, truth compressed into the time it takes to refresh a screen. But the universe does not operate on our schedule, and science cannot function at the speed of curiosity. 3I Atlas entered our solar system moving faster than any interstellar object we have ever tracked. It developed a tail, then a second tail pointing the wrong direction. Its brightness fluctuated in patterns that existing cometary activity models did not predict. Every measurement suggested behavior outside known parameters. And behavior outside known parameters requires extraordinary levels of verification before anyone with a reputation to protect will speak them aloud. Comment what you think is happening here, even one word. Mystery, process, science, just one word. Inside NASA, inside the European Space Agency, inside observatories from Chile to Hawaii, teams work with data so raw it looks like television static. A single image from the James Webb Space Telescope begins as millions of measurements of infrared light captured across 18 hexagonal mirror segments. But these raw photons are useless without transformation. First comes flat field correction. Engineers must account for how each individual pixel responds differently to light. Some pixels are more sensitive, others less. Temperature fluctuations change these sensitivities hour by hour. Every exposure requires comparison against calibration images taken under identical conditions. Then dark current subtraction. Even when the detector sees no light, electrons still accumulate. This electronic noise must be mapped and removed from every single measurement. The process generates gigabytes of correction files before you even begin analyzing the actual astronomical target. Cosmic ray removal comes next. High-energy particles from deep space strike the detector constantly, creating bright artificial spots that look identical to real astronomical features. Software must identify and eliminate these false signals without accidentally removing real data. For a faint, fast-moving object like 3I Atlas, distinguishing cosmic rays from genuine features becomes extraordinarily difficult. Background star subtraction completes the initial pipeline. 3I Atlas moves against a backdrop of thousands of distant stars. Each one must be identified, measured, and digitally removed. But the object's rapid motion means it appears in different positions across multiple exposures. Standard stacking techniques fail. Engineers must write custom software that didn't exist before this object appeared. This entire calibration sequence takes a minimum of 3 weeks. Not 3 days, not 3 hours, 3 weeks. And that's before any scientific analysis begins. The James Webb Space Telescope observes the universe on a ruthlessly efficient schedule. Over 400 research programs compete for observation time each year. Distant galaxies, exoplanet atmospheres, stellar nurseries, supernova remnants. 3I Atlas received exactly 47 minutes of observation time across 2 separate sessions. Then Webb moved on because a dozen other urgent requests waited in the queue. Those 47 minutes of photons now sit in computer systems at the Space Telescope Science Institute in Baltimore. But photons are not answers. They are raw material. The transformation from measurement to meaning requires human expertise that cannot be rushed. Hubble Space Telescope faces entirely different constraints. It orbits Earth every 93 minutes at 17,000 miles per hour. To photograph something moving as fast as 3I Atlas requires the telescope to track the object while simultaneously compensating for its own orbital motion, Earth's rotation, and the object's trajectory through space. Hubble's fine guidance sensors lock onto reference stars to maintain stability, but tracking a fast-moving target pushes these sensors beyond their design specifications. The system was built in the 1980s for observing essentially stationary distant galaxies. Its maximum tracking rate is 2 arc minutes per second. 3I Atlas, at certain points in its trajectory, moved faster than this limit. The telescope could point at the object but couldn't track it smoothly. Every exposure became a compromise between tracking accuracy and light collection. Engineers spent days calculating pointing solutions. Then weather interfered. Cloud coverage blocked ground-based confirmation observations needed to verify Hubble's data quality. Technical issues with data transmission delayed downloads. By the time everything aligned, the object had moved. The geometry changed. They started the calculations again. This is not failure. This is the reality of observing the universe with instruments designed for different purposes. A equals natural phenomenon behaving unusually. B equals something requiring new theoretical frameworks. C equals we need updated physics models to explain this. Comment A, B, or C. No wrong answers here. Ground observatories contribute crucial data but operate under constraints space telescopes never face. The Atacama Large Millimeter Array in Chile can detect molecular emissions from cometary tails, revealing chemical composition in ways optical telescopes cannot. ALMA observes at wavelengths between radio and infrared, sensing carbon monoxide, water vapor, and complex organic molecules. But ALMA requires exceptionally stable atmospheric conditions. Water vapor in Earth's atmosphere absorbs the same millimeter wavelengths ALMA detects. Observations can only proceed during periods of extreme dryness at high altitude. The Atacama Desert provides some of the driest air on Earth, but even there, atmospheric water content varies. Weather patterns determine when observations happen, not scientific priorities, not public curiosity. Weather. The European Southern Observatory's Very Large Telescope in Chile provided some of the earliest spectroscopic observations of 3.1 Atlas. Four 8.2-meter telescopes working in coordination captured light from the object and split it into component wavelengths. This spectral fingerprint reveals what the object is made of. But 3I Atlas presented unique challenges. Its trajectory took it into southern skies, favorable for Chilean observatories, but problematic for northern hemisphere instruments. As weeks passed, the geometry deteriorated. The object moved lower toward the horizon. Telescopes had to observe through increasingly thick layers of atmosphere. Image quality degraded. Spectral resolution decreased. Every additional degree closer to the horizon meant exponentially worse data quality. Astronomers requested additional observation time. Schedules were rearranged. Other research programs were postponed. Then they discovered the object was fainter than initial estimates predicted, or the brightness varied more than models suggested. They needed longer exposures, better atmospheric conditions, more time. But the object kept moving, further away, dimmer, eventually became too faint for ground-based spectroscopy. What you have is what you have. Now make sense of it. The Minor Planet Center publishes orbital updates every 24 hours. Position, velocity, trajectory. These numbers tell you where something is and where it's going. The public sees these regular updates and thinks nothing is happening. But orbital calculations are bookkeeping. The actual scientific work, the interpretation of what this object means, happens elsewhere. In laboratories where spectroscopists compare emission lines against databases of known molecules. In computational centers where researchers run thermal evolution models. In private email chains where scientists who trust each other share preliminary ideas that might be completely wrong. Those conversations remain private until consensus emerges, until multiple independent teams analyze the same data and reach compatible conclusions, until someone feels confident enough to risk their professional reputation on a public statement. 3I Atlas presents challenges neither Oumuamua nor Borisov created. Oumuamua, discovered in October 2017, was large enough and close enough to measure despite being spotted after it had already passed through the inner solar system. By the time astronomers realized it came from interstellar space, it was already leaving. But it left a clean trail of observations, clear trajectory, predictable behavior after perihelion. Borisov, discovered in August 2019, behaved like a normal comet. It showed expected chemical signatures: water, carbon dioxide, dust grains, matching solar system comet composition, familiar physics, predictable activity. Scientists understood it immediately. 3I Atlas does neither. It is smaller, fainter, faster. Its brightness changes show patterns existing models did not predict. Its tail morphology requires new interpretation frameworks. The anti-tail structure, pointing toward the sun instead of away, suggests large dust grains in unusual orbital configurations. But confirming this requires measurements current instruments struggle to provide. Its post-perihelion trajectory placed it in a geometric position where Earth-based observation became extraordinarily difficult. The angle between our world and the object creates parallax measurement challenges that did not exist for previous interstellar visitors. A tenth of a magnitude difference in brightness estimates translates into massive uncertainty about size, composition, and activity level. Does this change how you see our place in the universe? Does it matter that we can detect visitors from beyond, but cannot yet fully understand them? Behind the silence, work continues. Scientists combine spectral data from multiple observation nights, searching for consistent patterns in chemical signatures. They analyze how the tail evolved over time. mapping particle ejection rates against solar heating models. They test whether unusual dust grain size distributions could explain the anti-tail geometry. They integrate brightness measurements from dozens of observatories into curves that might reveal rotation periods. They compare thermal emission data from infrared observations with reflected sunlight measurements from optical telescopes. They build computational models of how ices sublimate under solar heating and compare predicted outgassing patterns with observed activity. Every dataset comes from different instruments with different calibrations. Data from Chile must be reconciled with data from Hawaii, from Spain, from space-based platforms. When measurements disagree, investigators must determine why. Different atmospheric conditions during observation, calibration offset between instruments, timing differences that capture the object in different activity states, or genuine variation in the object itself. The peer review process adds months to publication timelines. When researchers believe they have significant findings, they write papers describing methods, data, and conclusions. These papers go to scientific journals, where editors assign them to independent experts. These reviewers scrutinize every claim. They check calculations, question assumptions, demand additional analysis, request clarification on ambiguous statements. For 3I Atlas observations, reviewers demand comparison with alternative interpretation frameworks. They ask for statistical confidence levels on every measurement. They require authors to test and rule out competing explanations. The paper returns to authors with pages of comments. Revisions are made, additional analysis performed. The paper goes back to reviewers. The cycle repeats. This process typically takes 4 to 6 months for standard astronomical observations. For an unprecedented interstellar object showing behavior outside existing model predictions, reviews become even more rigorous. Only after surviving this examination does research enter the official scientific record. Only then can space agencies confidently reference it in public communications. NASA waits because history remembers mistakes. In August 1996, scientists announced possible evidence of ancient microbial life in a Martian meteorite designated ALH 84001. The announcement made global headlines, press conferences, magazine covers, books, documentaries. Then other teams examined the evidence. They found that the microscopic structures could be produced by non-biological chemical processes. The mineral formations could result from high-temperature events. The organic molecules might be terrestrial contamination. The extraordinary claim faded into scientific uncertainty. The researchers spent years defending their methodology. 3I Atlas carries higher stakes. An active interstellar visitor displaying behavior requiring new interpretation frameworks. Make a premature claim and you damage public trust in space science. Announce artificial characteristics for a natural object and you become the scientist who cried alien. Claim natural explanations when data actually points elsewhere and you potentially miss the most important discovery in human history. So they wait. Multiple independent analyses must reach compatible conclusions before anyone speaks publicly. When data transmission occurs between Webb and Earth, it travels at 500 kilobits per second through NASA's Deep Space Network. This network consists of massive radio antennas at 3 locations: Goldstone, California, Madrid, Spain, Canberra, Australia, positioned around Earth to maintain constant contact with spacecraft as the planet rotates. A single observation session from Webb generates approximately 58 gigabytes of raw data. At 500 kilobits per second, transmission takes 26 hours, not minutes, hours. And that's assuming perfect conditions with no interruptions, no competing spacecraft demands, no technical issues. The data arrives at the Space Telescope Science Institute, where automated systems perform initial integrity checks. Are all data packets present? Did transmission errors corrupt any measurements? Are instrument temperatures within expected ranges? This preliminary assessment takes 3 days because the systems must verify millions of individual data points against expected values. Only after passing these checks does data move to calibration specialists. These experts know every quirk of Webb's instruments, how the near-infrared camera responds to different target brightnesses, how the mid-infrared instrument's detector sensitivity varies across its field of view, how temperature changes affect measurement precision. They apply correction algorithms developed through years of testing. But 3i Atlas presents situations these algorithms were never designed to handle. A faint object moving faster than most asteroids, activity that changes between exposures, brightness variations that complicate standard analysis techniques. Custom processing pipelines must be developed, tested, validated against simulations before applying to real data. Small errors compound into massive misunderstandings. Parallax measurements, the apparent shift in an object's position as Earth moves in its orbit, require precise distance calculations. Get the distance wrong by even 2%, and all subsequent estimates of size, intrinsic brightness, and composition become meaningless. Thermal modeling introduces additional uncertainty. How much sunlight does the surface absorb versus reflect? How efficiently does it radiate heat into space? These properties determine whether observed activity comes from water ice, sublimation, carbon dioxide outgassing, or something else entirely. Wrong assumptions about thermal properties lead to incorrect conclusions about composition. Positioning uncertainties create cascading problems. 3i Atlas moves extraordinarily fast. A measurement delayed by 6 hours places the object thousands of kilometers from its actual location. Brightness measurements depend on exact geometry. Distance to the sun, distance to Earth, viewing angle, phase angle between sun, object, and observer. Miss any parameter by a small margin and your data loses scientific value. NASA publishes fewer announcements but maintains higher confidence in what it does share. This is not censorship. This is institutional responsibility built on decades of experience. When the data finally releases, when the press conference finally happens, when images finally appear on screens worldwide, what will we see? High-resolution photographs showing surface features if the object is large enough, and observations capture sufficient detail. Updated spectral analysis revealing chemical composition with quantified uncertainty ranges. An activity timeline mapping how tails develop, brightened and faded correlated with solar distance. Brightness evolution curves potentially indicating rotation periods or tumbling motion. Jet morphology showing where and when material erupted from the nucleus. Refined orbital calculations determining trajectory precision to within kilometers. But more than data, we receive context. Scientists explain what measurements mean, which features align with natural cometary processes, which features require updated interpretation frameworks, what new questions emerge, what observations future instruments must pursue. The public interprets silence as suspicious, as concealment, as evidence of conspiracy. But the silence is not secrecy. It is the methodical process of transforming measurement into knowledge. The difference between data and understanding. Future observatories will accelerate detection timelines. The Vera Rubin Observatory in Chile will begin operation soon, scanning the entire visible sky every 3 nights. It will detect interstellar visitors weeks earlier than current systems, track them continuously throughout their solar system passage, provide data in near real time to observatories worldwide. The era of discovering visitors too late will end. But even with better instruments and faster detection, analysis will still require time. Understanding will still demand verification, multiple independent observations, cross-checking between different measurement techniques, peer review, consensus building. Truth will still move slower than curiosity. Write one sentence starting with, "This means." NASA is not silent because they found nothing. They are silent because they found something, and they refuse to speculate about its meaning before they know. They choose accuracy over speed, verification over spectacle, knowledge over entertainment. In a world that rewards instant reactions and punishes patience, this approach seems alien, but it is the only approach that functions when stakes involve expanding human understanding of the universe. 3I Atlas will not be the last visitor. Statistical models suggest dozens of interstellar objects larger than 100 meters pass through the inner solar system every year. Most go undetected. Some will behave predictably. Others will surprise us. Each offers opportunities to learn about how planetary systems form, how planets eject debris, how matter moves through the galaxy over billions of years. But only if we observe carefully, only if we analyze thoroughly, only if we accept that understanding requires patience. The universe does not reveal its nature on our schedule. It reveals itself when we develop the discipline to distinguish signal from noise. When we become willing to say we do not know yet, instead of pretending certainty we have not earned. So tell me, what do you think happens next? What will the data reveal when it finally arrives? Maybe the universe is not hiding anything. Maybe we are just learning, slowly, painfully, how to ask questions that actually have answers